Phantom power is usually between 9 volts and 52 volts. Most consoles put it at 48 volts. The higher the voltage, the more the quality, or the better the quality of sound that goes through the microphone, okay? That's for phantom power. Now, why do we call it phantom is because phantom is ghost, isn't it? It's named for ghost. Every microphone that does not need phantom power does not see phantom power. You see it? If you have a setup and you have 6 condenser microphones and another 6 dynamic microphones, if it's a global phantom power, that means when you switch on phantom power, it goes to everything. The dynamic microphones that are not condenser simply continue working. They don't notice the phantom power at all. But the condensers will switch on. Do you get it? That's why it's called phantom power, because the phantom power is not seen by those who don't know it. It's not all of... How many of us have seen a ghost? But some people say they've seen ghosts, have you? Yeah, so only the people who are tuned to see ghosts see ghosts. The rest of us don't see it. The same thing with phantom power. Okay? All right. So finally, there's the wireless microphones. It's not very different from the dynamic microphone. The only difference is that there's no wire. The only difference between a wireless and a wired microphone is that there's no wire. What a wireless microphone does is they added a transmitter to the base of the microphone. So it takes your energy, instead of running it through cable, it converts it to radio frequency. And then you have a receiver at the other end where the mixer is, which converts it back into the normal audio signal. Do you get it? So that's the only difference. But all the characteristics, the cardioid effect, the bidirectional effect, and so on, they are all still embedded in the mic itself. Are you with me? All right. So I think we'll leave the topic of microphones now. If you have questions on this, you can save it for later, but write it down so you don't forget whatever questions that you have. All right. Let's move down the line. I said the first thing we meet is an input device, and we identified microphone as an input device. What other input devices can you think of? Apart from, somebody said instruments. Let's leave that. What other input devices do we have? Yes? A recorder. A recorder. A recorder. Okay, we need to break that down. A recorder, maybe an audio recorder. Let's look at the first. How many of us know the cassette tape? I'm sure we all met it before. Right now, nobody seems to use them anymore. I'm sure the children that are born now, when you say cassette, they will look at it and be wondering what it does. See? Okay. But the cassette recorder had a way in which it did the recording. It recorded on what do you call a celluloid, a tape, not so. But there's something there, what we call the playhead. Not so, a playhead. That's what the tape rolls over. And that's what magnetizes the tape. So the playhead is a magnetic device. So look at, when you talk about a recorder, if we're talking about tape, then there's a playhead. That will be the input device. Okay? What does that one do? Convert what? Electrical energy into magnetic? Not so. And then use that to record on the tape. What other kind of recorders do we have? Or what other kind of input device can you think of? An optical recorder, like your CD writer. What media does CD writer use? Do we know? Who can give me a guess? Wow. Well, have you written a CD before? How many of us have burnt CD before? And they give you a CD and you've burnt your own CDs. Did you ever wonder how it is recorded on the CD? Okay, I'll tell you briefly. A CD uses a laser beam. Do you get it? You'll see that when you look on the surface of a CD, a compact disc, it looks like a mirror, isn't it? Yeah, there's a film at the bottom of the CD, which is like a silver film, okay? Now, there's a laser beam on what you refer to as a playhead in a CD player, which directs the beam onto the CD. Now, it does two things. It can read what is written on it, or it can itself write on it. Now, you know you can't write on just any CD. You have to write on a recordable CD, which means the one that has a media in which you can actually do recording on. Do you get it? It's still the same laser beam. You get it? But it goes in the reverse direction. Instead of reading, is the one sending out. Okay? So that's like an optical transducer. Do you get it now? So that's the way the CD works. It's laser. Some time ago, we had what we call the laser disc. Some people tried to do it commercially, but the thing didn't catch. The CD was much smaller. There was one that was smaller than that too. I've forgotten the name now. That was much smaller than the CD, but came in a case, just like the CD itself. I've forgotten the name now. Yes. No, it wasn't that. It had a name. Yeah, it's smaller, but in a case. You know, the CD itself is just a disc. But that smaller one was in a case by itself. We thought that one would even take over from the cassette, but it didn't. At the end of the day, it was a CD. And now everybody has gone to USB and flash drive and stuff like that. Nobody even thinks of CDs and floppy drives and all of that anymore. I mean, it wasn't a floppy drive. You met floppy drives. Interesting. Diskette, right. The initial one was a big one, almost the size of a CD. And then it turned to the 3.5-inch diskettes. And then those ones went out for compact disk and CD-ROM drives. And now we are in the flash drive era. Okay, so those are input transducers. Those are the type of transducers that you can have. All right. After the microphone, what comes next in your sound system? For those of us who have set up sound system before. Cable, okay. But let's jump the cable because the cable is between all of them. What's next after the microphone? Mixer. Abi? Mixer. There are different types of mixers. Most of the time, you plug all your inputs into a mixer. Some are what we call the box mixers. I don't see any of them around here. They're like a small box. You plug your microphone at one end, plug your speaker at the other end, speak into the microphone, and you hear it from the speakers. Not so. Right? Huh? Mixer amp. That's what they call it. That's a type of mixer. There's also the other type that's by itself. You plug your microphone into it. You still have to plug some other things before you get sound out of your speakers. Not so. Okay? So the mixer is the next item. When it comes out of a mixer, where does your sound go to? Processor. Okay, let's keep the processor. After the processor, amplifier. That is another major component. Now, what I'm saying is the basic sound system must have these ones for it to work. If you don't have these items, you will not get the sound system to work. So we mentioned the amplifier. What does the amplifier do? It amplifies. Abi? Simple answer. Not so? It amplifies. That's why they call it amplifier. Okay, I just want to talk briefly about the amplifier. A lot of us have some wrong concepts about amplifiers. The power amplifier as it is, we'll come back to the other devices. I just want to talk about amplifiers briefly. The power amplifier as it were is a black box, usually with two knobs, not so. Just two knobs on the front of it. And that's because most of the amplifiers are made, the laymen call it stereo. They are dual power amplifiers. It's two amplifiers in one, usually. They make the single amplifiers too. Do you understand? Depending on what you want. But usually they do two. So you have a channel 1 and a channel 2. Most of the time you can operate the two channels on an amplifier independently. In other words, if you have an amplifier with two sides like that, you can use one side to run the house, what we refer to as the house. That's the speakers that are facing the congregation. And use the other side to run the monitors. That's the speakers that are facing the ministers. Do you get it? So in such a way, you can use an amplifier in two ways, right? In other forms, you can do different things with the amplifier. But I just want to mention, usually, an amplifier has what we call a gain. Gain. Gain means it takes one signal coming in and then amplifies it. The way it amplifies is what we refer to as gain. Do you get me? So gain. Now, depending on how much gain you have, the sound goes out at the other end. But when you want to buy an amplifier, what do you look for? When you are buying an amplifier, what do you ask the person who wants to sell? Wattage, thank you. That's when we refer to it as power amplifier. So you want to know what power amplifier has. Power is referred to in terms of wattage. I've seen people call me, we need a very powerful amplifier. I want a 5,000 watt amplifier. Not so. That's what we say. So the wattage is what is important first in an amplifier. But for us engineers, the wattage means nothing until you know into what load that amplifier is going to present the wattage. Let me explain. There's another phenomenon that you need to worry about when you're talking about amplifiers, a choice of amplifiers. It is the impedance of your sound system, okay, of your speakers. Do you get it? Now, most speakers will have impedance ranging between 4 and 16 ohms. Between 4 and 16 ohms. Now, an amplifier does more work when the impedance is lower. Do you get it? So an amplifier working into a 16 ohm load will do more work when it's working into a 4 ohm load. I don't know whether you understand that. The higher the value of the impedance, the less work the amplifier does. The lower the impedance that the amplifier sees, the more work the amplifier does. Now, I've seen, for those of us who are professionals, we look at, we say, okay, we can drive the amplifier at 2 ohms. A whole lot of people think they can do that. But you know what happens to the amplifier when you are driving it at 2 ohms? It gets hot. Most amplifiers will get hot. Do you get it? And if you drive for long at 2 ohms, the amplifier soon gives up. Almost every system that you use generates heat. But heat in itself is like fire. You know, you can have heat without fire. But it's like fire. The hotter a device gets, the more likely it will break down. Do you understand? Your laptops have, what do you have inside them? A processor. Now, for those of us who have looked inside a laptop before, you have a fan bolted to the processor, right? Your vehicle engines have what? Radiators, and they have fans bolted to the radiator, which means as they work, they generate heat. The same thing with our audio amplifiers. They generate heat. Do you get it? Now, the harder they are working, the more the heat that they generate. So most of the time, you need to channel the heat away from the amplifier. Now, most of the power amplifiers we use now have fans in them, not so. But some don't have fans. Have you noticed that before too? Like the box mixer. Most box mixers don't have fans in them. But what they have is what we call the fins. You see at the back, they have a heat sink that looks like fins of metal. The idea behind that is when the amplifier gets hot, those fins are right against the transistors that get hot, so they conduct heat away. Do you get it? They conduct heat away. So you don't want to put an amplifier in a place where there's no air, where there's no airflow. Even the ones that have fan, if you cover the fan with the more modern ones, you'll see a light come on showing high temperature. Once an amplifier shows temperature, it will shut down. Now, if it doesn't shut down by itself and the heat makes it shut down, then it might not work again. But if it shuts down by itself and it cools down, most of the time you can get it to start again. especially in the region of the Ahujas. You keep your questions. You ask later. So that's the case with the amplifier. Now, one more thing to mention about the amplifier. Those knobs in front, what do you call them? The knobs in front of an amplifier. You know, I told you there are two knobs, Abi. What? Volume control. Did you hear that? Sensitivity control. We call them volume control, right? And I say that that is a wrong name for those controls. We call them attenuators. Attenuators. You know why they are attenuators? For volume control, it means you can change the volume, right, of an amplifier just by turning the knob. But with a normal amplifier, you don't change the volume that way. You only reduce the sensitivity. Why do I say this? If you reduce the sensitivity of an amplifier, turn the volume knob all the way to almost closed. All the way to almost closed. All it needs is for the input to get high enough. The amplifier will deliver the full power. Let me paint a scenario. You have a 5,000 watt amplifier, right? And you have speakers that are 2,000 watts. So you say so that the amplifier doesn't burn the speakers. The amplifier can burn the speakers, 5,000 to 2,000, isn't it? But because you don't want it to burn, so you turn down the volume control. She? Aha. Now, it's volume you turned. Then I go to the mixer, and I think it's not loud enough, so I push the volume. What do you think happens with the amplifier? Do you think it will stay with the low volume that you put it? It will deliver its full power to the speaker. So the fact that you turn down an amplifier does not mean that it won't burn your speakers. I don't know whether you understand what I'm trying to say. It's just a sensitivity. All you need is more volume, a higher level of signal input for the amplifier to still deliver its full power. And that's why when they write around it, they don't write 1, 2, 3 like they do in your home sound system. They put -6, -3, 0, +3, +6. Do you understand? So if you put it at -6, all it needs is a +6 to get it to 0. Do you get my point? If you put it at -3, all it needs is a +3 to get it to 0. So if your signal level is at +12 and you put it at -6, that amplifier will deliver full power. You get me? It will deliver the whole 5,000 watts into the load that you've connected to it. So don't be deceived by saying you reduce the amplifier, so therefore the amplifier will not burn your speakers. You need to make sure that the other things coming in are also reduced. Do you understand? If you have more questions, we can ask about that later. Now, there are input sides and output sides to an amplifier. Usually on the input, you can have a variety of connectors that you use for the input. XLRs, jack plugs, not so. XLR and jack is the most that we use. But there are some older systems that actually use wire, bare wire as the input. Now on the output, you have, what do they call them now? Binding posts. You know binding post? Binding post has a prong. You tie the wire to it or screw something down on it. That's what they call binding post. It's just something you bind something to. Do you understand? So you can have binding posts. Some will tell you 5-way. You can have a banana plug. You can just tie the wire to it and all that. Then there's a modern technology. It was modern about 12 years ago. Yeah, about 12 years ago, it became modern. The speak-on plug. I'm sure some of us have seen this speak-on plug. Yep, if we look at the back of that. There. That is referred to as a speak-on plug. When I first started sound, I was used to the home kind of sound system where we take red wire and look for the place that has red knob and we push the wire in, press it down, push it in, and a hose wire, not so. And then the speaker that came in had, believe it or not, XLR. Only XLR. We know what XLR is, don't we? Only XLR. And it was the 3, XLRs have 3 pins, not so. So it was like, okay, so where does the wire go? Nobody told me about it before. And the speakers came newly. Program was going to start in an hour. So you can imagine how I panicked. Started looking for books on what to do and all that. At the end of the day, I thought about it. Let's do something. We put on the amplifier, took 2 wires that came out of the amplifier, then pushed one into one hole and pushed the other into the second hole. It didn't work. Okay, we remove it, put it in the third one. That's how I found how the XLR worked. It was Carlsbro. In those days, Carlsbro was new. But that's how we ran the program. So when we found the 2 that worked, we used broom to hold the wire in place. We used a broomstick to hold the wire in place. And that's how we ran the program. Nobody questioned me because nobody knew any better. After that, it was then I learned that loudspeakers could also use XLRs as their input connectors. Now, I think since then they stopped. They now use speak-on plugs. Now, the thing behind XLRs is that, to an extent, you can just pull it out. But after that, the next set of XLRs had buttons that you need to press. They had a notch at the tip, so it doesn't just pull out. But speak-ons were better, because when you plug a speak-on, you twist it into place. So nobody can accidentally remove a speak-on. If you don't know how to do it, you can't unplug a speak-on. I'm sure when you first used the speak-on, you had that experience too, for those of us who have used it before. There's a knob that you pull, and then you turn. Okay, so that's that with amplifiers. Let me see, is there anything else you need to know about amplifiers? Oh yes, some have some other devices attached to the back of the amplifiers. I don't know whether they still do that now, but PV in those days had these crossover things inside them. Yamaha also had crossovers inside them, so that in an amplifier, apart from amplification, it also did crossover functions. So we'll leave that. We're going to talk about crossovers and other filters in a few minutes. Write down your question. I've spent 40 minutes already. Oh, my goodness. Thank you. Okay, so we'll quickly treat the other 2 that I want to talk about, loudspeakers and mixers. Mixers first. Mixers have, what do they do? They mix. Mix. What do they mix? I have a Kenwood mixer in the kitchen. So I mix dough with the Kenwood mixer. Oh, your mixer does mix audio signals. Now, what kind of audio signals does it mix? When we say mixer, what is it mixing? It's mixing what and what? First of all, at the lowest level, what does our mixer do? It mixes microphones and instruments. Not so. Microphones and instruments. Why does it need to mix microphones and instruments? Have you heard a choir without PA? When the choir is singing without PA, have you heard how they sound? If the choir was here and the PA went off, they were singing and the drummer was drumming, and then the keyboardist was playing, what do you hear? You hear their voices. Abi? At different levels. You hear what else, again, apart from the voices? You hear the drums. Because you can hear the drums with or without amplification. Not so. Do you hear the keyboards? No. Do you get it? Now, it means naturally, all of these inputs have different levels. Do you get it? But the person who is listening outside of the window hears only what's coming out of your speakers. Do you get it? It's not like you that's here. You know, you can see the drummer spending all his energy, making as much noise as he's able to. You know, some of them, when they come and they eat a lot of food before they come and drum, so that drum must sound very, Abi? But you hear all of that, as well as the voices. And then the lead vocalist is struggling to be heard. Now, the work of the mixer is to bring all those levels under control so that anybody that's hearing what's coming out of your system can pick out all of those elements. Are you with me now? All of those elements. That's what a mixer primarily does. But it does a lot more than that as well. Are you with me? A mixer is also a routing device. It routes. It sends signals into different places. Okay? When you want to buy a mixer in your church, what do you say? You want a 24-channel mixer. Abi? But do you think of how many places you want to send signals to also? Let's look at what we have here. Okay? If we have a mixer is sending out signal into that, isn't it? It's sending into that one as well. And it's sending into all of these ones. Right? Now, depending on how many separations you want, separations meaning, for instance, let's look at it. Those two in front, we probably use the same signal. You put the same thing in them. Those four behind it, we have another signal in it. Not so. And then these ones below here, maybe another output. Sure? The four of them can be on the same output. Those ones there by the keyboard, a different one again. Not so. How about the one beside the drummer? Now, supposing you were to put the sound that's coming out of here is what is coming out of the drum monitors. You think the drummer will be very happy with you? He won't be very happy, I can imagine. So basically, you want a mixer that's able to send that many number of signals out. Not so. And then you now mix what is going on into each one. Let me explain. The person in front might not want to hear saxophone at all. You understand? Might not even want to hear the rest of the drum kit, just the snare. And might want to hear the singers in that monitor in front. So you need a mixer that's capable of doing that. Do you get it? So you can stop these signals and allow these other ones to go through. Okay? So that means when you are purchasing a mixer, you want to also know how many outputs that you can get out of the mixer. And that's what they refer to when they say a 27-bus mixer. Each output is a bus. Do you get it? Some will have auxiliaries. Maybe the most common is 2 for the cheapest ones. Then some 4, some 6, and some as high as 16. And the current digital mixers up to 32 auxiliaries. Some of the digital ones, you can configure them the way you want. It tells you it has 40 buses. So you can decide you want to use 16 of it for auxiliaries, you want to use 8 of it for group, and maybe 2 masters, and maybe 3 or so for matrix, until you get to the count of 40, if it's 40 that it has. Okay? That's the difference between the digital and the analog mixer. So I've told you, a mixer does what? Level control, balancing your levels, right? It also does routing. And it does something else too, equalization. The one you refer to as tuning. When you have a sound source and there seems to be so much bass inside it, what do you do on the mixer? You remove the low frequency, remove the bass. And if the thing is not sharp enough, what do? You increase the high frequency. So there's an equalization function. Now, depending on the kind of mixer you have, there are a few other facilities that you can get inside the mixer. Okay? So let's leave the mixer for now. If you have questions on it, just hold on to the questions. Let's see, there's something else I wanted to mention about the mixer. Okay, let's leave it. What's the other thing now? Processors. Processors. Now, these ones I like to refer to as peripherals. Peripherals means without processor, will your system work? How about the rest of us? Those who are not sleeping. It will work. Thank you. So, but why do we need processors? Quality. Okay, to change the quality, right? You could say that. But somebody will say, okay, you need processors to process. All right. All right. What kind of processors can you think of? Let me mention a few. We have crossovers, compressors, limiters. Anything else? Equalizer. It's a processor too. What else? Sound effects. Okay? Yeah, let's admit sound effects as processors too. Okay? There's still something else. How about gate? Gate. Gate. Okay? Anything else? Well, the rest are just combinations, you understand, of these things that you just mentioned. We mentioned a gate, limiter, there's a docker. Now, that usually comes into evac systems, evacuation systems, we call it. So that, okay, if it's playing music and you need to do an important announcement, once you start making the announcement, it pulls down the music. That's what a docker does. Once it sees an input on it, it pulls down everything else so that what you are inputting now becomes priority. That's a docker. There's an automatic gain control, which does both expanding and compression and limiting. Okay? That's why I said it's a combination. Okay? Let's look at them one by one. The first one is an equalizer. Somebody mentioned equalizer. That one you see is a standard in everything. You always equalize. Equalizers have two main types. There's what we call the graphic equalizer, and then there's the parametric equalizer. Are we still together? Graphic equalizer. How many of us know what graphic equalizer is? If you know about it, so I don't need to talk about it. Okay. Graphic equalizers are the type you see all over that have these several knobs that you slide up and down. Why do we call it graphic equalizer? Whatever you equalize, you see it graphically. Do you get it? You see it graphically. So when you are increasing the low frequency, you are reducing the mid, you are increasing the high frequency, you can see that smile. You will see it drawn on the surface of the graphic equalizer. Okay, I'll just tell you something briefly. For an equalizer to work, you change three main parameters on the equalizer. First one is the frequency. Second one is the gain of that particular frequency. And the third one is the bandwidth. Now, I will quickly go into a little bit of music for you to understand what we're talking about. Normally, I start with that, but we don't have that much time. That's the physics of sound. In sound reinforcement, we talk about frequencies, not so. Frequencies, and we talk about volumes. That's amplitude. The human being is able to hear sounds when his or her ear has not been damaged. I'm sorry to tell all of you here, your ears are damaged. There's nothing we can do about it unless we go and get born again. This time, not the born again of water and fire. So you have to get born again properly. Why do I say that? When you're still a baby, your ear is extremely sensitive to everything. As you grow older, you've subjected your ears to noise and all of that, and your ears are shut down in some particular frequencies. If you want to test the truth of what I'm saying, go into a lab and check those frequencies from 20 to 20,000 hertz. You'll find that by the time you get to 16, you don't even hear it anymore. And by the time you get below 40, you don't hear it anymore. Are you with me? But a normal, undamaged human ear is to hear from 20 hertz, 20 cycles per second, to 20,000 cycles per second, 20 kilohertz. Now, along the way, we also noticed that our ears don't hear all the frequencies the same way. In other words, let me just simplify it. I'm oversimplifying it. Our ears are more sensitive to the mid-range. So when you are pumping something, the volume of something in the mid-range at about 10 dB, for instance, and then you do high frequency at the same 10 dB, the human being is going to tell you that that high frequency is not at 10 dB. You understand? It seems lower than 10 dB. You understand what I'm trying to say? The same thing with the lower frequencies. You need to push them up higher than normal for us to hear at the same level as we're hearing the mid frequencies. Now, because our ears are very sensitive to that, most of the time when you tune an EQ, when it sounds nice, what does the graphic EQ look like? Looks like a smile, isn't it? You pull down the middle. When you pull down the middle, the sound seems to sound very good. Not so. That is to show you that your ears are sensitive to that mid-range. So you want to pull it down so that it doesn't sound harsh to you anymore. I hope you understand what I'm trying to say. But that usually doesn't work well for a sound system. Because by pulling that down, you are going to also pull down the sensitivity of where your human voice is. So if you pull down the mid-range, you are going to find out that you're hearing and you're hearing, but the middle one that makes it clear, that makes what we're trying to say clear, you don't hear it. Are you with me? Okay. Now, why did I go into all of that? When you look at your graphic equalizer, the lower frequencies are on the left. The higher frequencies are on the right. And the mid frequencies are right in the middle. Now, depending on how professional the equalizer is, you can have as many as 31 sliders. So we call that a 31-band equalizer. Now, how many of us are musicians? You play music. You play music also. You too. Okay, you know what an octave is. For those of us who don't know, when you sing do, re, mi, fa, sol, la, ti, do, that's an octave. Do, do, that's an octave. Now, the human ear can hear 10 octaves. Are you with me? 10 octaves. Now, that 10 octaves is contained between the 20 and the 20 kilohertz. Are you with me? So what we do in equalization is we break down those frequencies into as many places as we want. You can do it in 4. When you have a 31-band graphic equalizer, it has broken it into 31 different places. Okay? Now, remember I said frequency and what? Gain. Those are the two parameters that change in an equalizer. The last one is called bandwidth. Bandwidth means when you are sliding, when you are taking up one slider, how many other frequencies is it taking along with it? If the bandwidth is 1 octave, it means it's taking a whole octave with it when you are raising it up. So it's not taking only that one frequency, it's taking up the lower frequencies and higher frequencies up to 1 octave. What is an octave in terms of number? Oh? What's octave in terms of number? For instance, I said human ear hears 10 octaves, not so. But I said you can hear between 20 and 20,000. So if I have a frequency of 20, what's an octave on 20? 40. Do you get that? An octave on 20 is 40. What's the octave on 40? It will be 80. Octave on 80, 160. Now, if you count it, you'll see you get only 10 by the time you get to 20,000. Check it yourself. I'll give you that exercise. We won't do it in class. Just check it yourself. You'll see that it's only 10 octaves. Are you with me? So when you look at a graphic equalizer that's 31 band, they'll tell you it's a 1/3 octave equalizer. That means for each octave on that equalizer, you have 3 knobs to change. Are you with me? So it starts from 20. So the first octave is 20 to 40. Gives you 3 sliders. So you have one at 20, one at 60 something. One at 20, one at 32, and one at 40. Then between 40 and 80, 3 sliders again. Between 80 and 160, 3 sliders. Between 160 and 320, on and on till you get 2. And that's why you have only 31 or 30, you understand, on that equalizer. You look at it yourself when you go. But in terms of numbers, an octave is a doubling of frequency. Doubling of frequency. So 440, 880 is the octave higher than 440. Do you get me? All right. So now, that's graphic. Parametric EQ. The difference between the graphic and parametric is that you see the graphic EQ graphically. The parametric EQ you don't see. But you look at where your knobs are. Are you with me? On most mixers, what you have is a parametric EQ, but not fully parametric. It's a sometimes just high and low. Sometimes it's what we call a semi-parametric EQ. What does that mean? It means you can change all the 3 parameters in a parametric EQ. In a graphic EQ, you can only change 2. No, you can only change 1 parameter. Gain is the only thing you can change. The sliders are already fixed for you. In other words, the frequencies are fixed for you. And the bandwidth of each one is already fixed. You can't change it. But in a parametric, you can change the frequency, you can change the gain, you can change how loud that frequency is, and then you can change the bandwidth. Because you are sound engineers, you need to learn that. That's why I'm emphasizing it. If you go to your mixer, you look at the EQ section, you see the high, mid, and low. Not so for the more professional ones. And for the even more professional ones, you see the high frequency. You see the mid, the frequency, the gain, and you see a bandwidth knob for the high mid. You see another one for the low mid. And then maybe the low, we have what they call it shelving. You have the frequency and have the gain. Why doesn't it have bandwidth? You notice I said the high doesn't have bandwidth. The low does not have bandwidth. The high mid and low mid have bandwidth. In other words, 3 knobs for each of those bands, right? Why don't the high and the low have bandwidth? What do you think? If you understand what graphic EQ is all about, what do you think? That's one good point. For the low, you cannot go below the 20, not so. But it depends on what frequency that low frequency is set at. Do you get my point? Okay. Now let's look at it this way. At the extremes of the spectrum, right, at the low end and at the high end, those knobs simply carry everything beyond it. But in the middle, that's the high mid and the low mid, you are still in the middle of the other ones. It's not at the edge. Do you get it? So those edge ones, we call them shelving EQs. Shelving EQs. What it does is it shelves everything beyond the frequency where you set it. So if you set it at 80, everything below 80 for the low frequency is shelved, is reduced. Once you turn it down, it reduces all the frequencies. Whereas the ones in the low mid, whatever frequency you set it to, the bandwidth around that frequency is what it reduces. Do you get it? Not everything below. Only that bandwidth. Do you get it? Only that bandwidth. That's why when you look at a graph of EQs, when they're showing you what it does, you see the shelving is drawn like that. But the other one is drawn like a bell. The high mid and the low mid is drawn like a bell. Then the high is just drawn up or down, depending on what you're doing. You understand? So you can have them, you see the down, you see the 2 bells, and then the one that seems to go up. So the low end, when you turn it down, you're shelving everything. The high end, the same thing. When you turn it up, you're raising everything too. That's why they call it shelving. But the middle ones, we call them band pass. Band pass. The frequencies below it, the frequencies above it, it passes them. So the only ones that you operate on are the ones in that particular frequency range. That's why we call it band pass. And that's why, because it's a band pass, you understand, you can select the band, how many frequencies it takes along with it. When you are raising it, how many frequencies it raises with it. Do you understand? Now, there's also what we call a notch filter. Notch filter. Notch filter. What does that do? You are able to zoom in on a particular frequency and either increase or reduce that. Which brings me to, what do you use an equalizer for? We've talked about what an equalizer is, not so? You can raise high frequency, you can raise low frequency, you can turn the mid. But what do you use it for? What are the uses of an equalizer? An answer? Anybody? What do you use an equalizer for? What does an equalizer do? What is the usefulness of an equalizer in a console? To filter sound. But why do you want to filter sound? We did say sound reinforcement, isn't it? No. When did I start?
Started around
12:30. And I had 2 hours. Aha. Abi? Yes. We started at 12:40. Hey, I've been corrected.
12:40.
Yes, so we have till 2:40. Thank you. Okay. So, where were we? What is an equalizer used for? Somebody said to filter sound. And I said, why do you want to filter it? I said it's sound reinforcement, isn't it? You want everybody to hear exactly what's coming out, isn't it? So why do you want to filter it? Tell me. Okay. Okay, I need to amplify that for him. He said, so that the way I'm talking, we can hear it like that at the other end. You understand? Now, what I'm going to say is this. Sometimes you want to filter some things. Maybe the sound source that's coming has a lot of low frequency in it. There's a lot of that you don't need. You understand? You can use an equalizer to remove that. Are you with me? Now, supposing maybe your speakers, the high frequency portion of it is not working very well. So somehow you need to tone that down. You can also use an equalizer to do that. Are you with me? But the final thing, no, it's not the final thing. There's one more thing that you use an equalizer to do. Your sound that you're hearing out of your system is a result of what is coming out of the speakers and what the room is doing to the sound. How many of us have tried singing in the bathroom? What does it sound like? You enjoy your own voice, don't you? You feel like a singer in the bathroom. Why don't you feel that way in the parlor? When you sing in the parlor? Do you understand? In the bathroom, the walls are talking back to you. What we call a reverb. Do you get it? They're talking back to you. So it's as if your voice itself is amplified that much further. Do you get it? Now, in the parlor, the furniture is absorbing your voice. As you are singing, it's going into the furniture and the thing is just not giving it back to you. That's where the difference. So you are left with your voice only. How many of us have attended a concert in the amphitheater? And you've attended a concert inside here. What do you think? What's the difference between, did the sound seem different inside here and outside there? Why do you think that is so? Thank you. Outside is all stone. Inside here, you have a lot of foam padding. You get the difference. The only thing that makes a major difference is when that hall is full of people. It sounds very close to this place when it's full of people. And they will tell you, any professional will tell you that human beings are like the best absorbers of sound. Do you get it? So now, that's to tell you that the room does interact with your sound. Are you with me? So now, if the room is interacting with your sound in a way that is not pleasant enough, then you can use your EQ to manage that interaction. Are you with me? If the room, there are what we call room tones and room modes. The mode for a room is the frequency that most closely matches the dimensions of the room. If you have your room at 17 meters, for instance, that's about the wavelength of a 20 hertz signal. So when you are playing music in there, you are likely to get a standing wave at 20 hertz. Let's assume that you can hear 20 hertz. Or for better purposes, if it's 34 meters. And it's a shear wall on both sides. So a wave of 34, a wave of 34 meters. There's no wave at 34 meters. That's the 10 hertz signal. A 20 hertz signal is 17. Not so. So a 40 hertz signal will be below that 17. So you can have a standing wave, you understand, at that frequency. In other words, in the room itself, you have that low frequency just sitting there, not going anywhere. Do you get me? Not going anywhere. Or in extreme cases, you just see that the room has a lot of bass in it. So you use an equalizer, locate those frequencies, and use an equalizer to reduce those particular frequencies. Okay? So you use a room to adjust the sound. An equalizer to adjust the sound of your system to match the room characteristics. Okay? And the final one is use an equalizer to remove or reduce feedback. Okay? What do you mean by feedback? What do we mean by feedback? We've all heard feedback before, haven't you? When somebody brings a microphone and faces a speaker with it, you hear one unpleasant sound. That is a feedback. It is unpleasant. You don't want feedback in sound. Not so. So you want to do everything to avoid feedback. So you use an equalizer to reduce. Now, why are you able to do that? I will tell you this. You can read more on it if you like. Feedbacks usually occur at a frequency that has reached what we call unity gain. It has reached a point where it is self-sustaining. That's when it will occur. Usually it won't occur at many frequencies at once. It starts with one particular frequency. You understand? So if you can identify that frequency where the feedback occurred, then you can pull down that particular frequency using your equalizer. That way you get what we call more gain from your microphone. In other words, you get more volume out of it before it starts howling. By the time you raise it again, it will start howling at another frequency. Are you with me? So you can use your equalizer to adjust that too. So an equalizer can be used for feedback control. Okay? So those are the uses of an equalizer. So the one on the mixer that's attached to a particular microphone, that particular channel, you can use to modify how that particular source, maybe a voice, maybe an instrument, comes out of the system. Okay? So that's an equalizer. Right. If you have questions on that, just keep that too. Now, the next one on our list, which is the next one? Crossover. 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 I believe our time is going, so let's look at, I'll quickly say what a crossover does. If you look at that speaker there, the naked speakers in it, how big can they be? How big are the speakers inside there? They're like 8 inches or 10 inches. They're actually 10 inches, I know. How about the speakers in here? You can see it, isn't it? How big are they? They are 18, okay? Those are, for some years now, they were the biggest. Now, manufacturers are making bigger ones, 21-inch and 24-inch. Yeah. There are now commercially available subwoofers that are 21-inch and 24 inches. In fact, 21 is available almost everywhere now. It's 24 inches that are still rare. You can get 21-inch, okay? Now, you know, by virtue of just seeing, that the same sound that this can produce is not the same one that those ones can produce. By virtue of the size. Are you with me? by virtue of the size. So now, if you don't have any way of separating what goes into each of them, and you just take output from your mixer and send to all of them at the same time, what do you think would happen? That one will be struggling to produce high frequencies. Those ones will be struggling to produce low frequencies. Are you with me? And, oh, yeah, we haven't talked about speakers. And in the process, something will die. Now, notice this always in terms of energy. Energy cannot be destroyed. It usually gets converted from one form to the other. So look at this. Look at it this way. If I keep expecting these guys to produce high frequency, they cannot produce high frequency, but I keep pumping high frequency energy into them. What do you think happens to the speaker? What happens to the energy first? It stays in the speaker, not so. Now, because it cannot be reproduced into sound, it changes to another form. What form does it change to? Heat. It becomes heat energy. Do you get me? So I'm pumping high-frequency signal into this at high level. The speaker is not able to produce it, so it's getting hot. What do you think will ultimately happen? The coil will burn. Do you get it? The coil will burn. Why? Because that energy converts to heat and is not going anywhere. It's staying in the coil of the speaker. So the end result is damaged woofer. You say, how come? How can high frequency damage low frequency speakers? That's how it does. If I keep trying to pump low frequency energy from those ones, same thing, only in reverse. This time around, the low frequencies changes into two forms. Changes into heat, but also into motion. Do you get it? The smaller speakers are struggling to produce low frequency, so they are moving further than they are meant to move. So what happens is the coil travels too far in the gap that was reserved for it. When it goes out, the cable breaks. So that speaker doesn't work. But what happens with the high frequency also happens to those ones too. If, for instance, the high frequencies, the tweeters are bad, and you are pumping it up and trying to get it to produce more high frequencies from the 10-inch woofers, that high frequency is going to turn to heat. And before you know it, the woofers will stop working. When you look, you see the coil would have turned black. Do you get it? So even without overdriving, you can actually still destroy your system. Do you get it? Simply by pumping what doesn't go into them. Now, why did I go into all of that? That is what a crossover prevents. So what a crossover does is to take the different signals, the low frequency, it will separate them and send it to low frequency speakers. It will take the mid frequencies, send to only the mid frequency speakers, take the high frequencies, send to the high frequency signals. Do you understand? Okay, within those speakers, I'm going to try to jump all of them together. Now, you can have a three-way system, a two-way system, a three-way system. Those are the most common. But you have also four-way and five-way systems. What do I mean by that? This speaker here, if you look at that one sitting there in the center of the floor, I don't know what it's doing there. Why is the speaker sitting in the center of the floor? For the drum class. Aha, I thought it would look strange. Anyway, if you look at that speaker, you will see it has a 15-inch driver like this. Also has a horn. Not so. That will be referred to as a two-way speaker. Do you get me? As a two-way speaker. So it has the high and the low. Are you with me? High and low. Now, this system here, you could refer to as a three-way system. Are you with me? That the high is right down the center. You can see it. It has these fins on it. And then the mid are on the sides. There's a reason for that too, by the way. I hope we'll be able to cover it in the class. There's a reason for it being like that. So there's the mid on the side, right? And then you have the lows right here. So it's a three-way system. Now, it means we need a three-way crossover to work on this system. So the crossover separates high frequencies and sends it to those high-frequency drivers, mid-frequency, and sends it to those mid-frequency drivers, and then low frequency that sends to these drivers. Do you understand now? So that's the work of a crossover. Now, there are two types of crossovers. There's the active low level and passive high level. Active low level and passive high level. I'll explain. Inside there, if that is a non-powered speaker, if it's a normal passive speaker, that's the one that doesn't have amplifier inside it. You understand? Normally, you put only one cable inside it, but you get both high and low from the speaker, right? Now, inside that speaker, there's a crossover network, a panel that has all these transistors and everything on it, transformers and condensers on it. That is called a crossover, but it's a high-level crossover. Do you get it? So what's coming from your amplifier gets loaded into that crossover, and the crossover is the one that now separates the one that goes to the tweeter or the high frequency and the one that goes to the low frequency. Do you get it now? So that's the crossover, high level, passive. Why is it passive? You can't adjust it. Do you get it? Good. Now, over there, there's another one that looks, you need to put power in it, called an active low-level crossover. Now, at the earlier days of Living Spring, the director himself actually produced, before it became commercially available, what we call the active filter. The active filter, whose job is the same as that device that you're seeing there on the table. What it simply does is it takes your signal from the mixer and separates it into high frequency, mid frequency, low frequency, how many ever ways that you want to do it. If you want it 4 ways, if you want 5 ways, the crossover will do that, the active. Then you now take the output of that crossover into the amplifier. Do you get it? So you have one amplifier driving tweeters, another amplifier driving mid-range, and another one driving subs. And if it's 4-way, one will drive the high, one will drive the high mid, another one will drive the low mid, and that one will drive the low. Do you get it? That's the case for active. So active crossover is before the amplifier. Passive high level is after the amplifier. You see the reason for the high level now? The power coming out of the amp is a lot of power, isn't it? That's what the passive works on. That's why we call it the passive high level. Whereas a low level is a low level signal coming out of your mixer. That's what the active low level works on. Okay? That's what the crossover does. So there are what parameters you see in a crossover? Frequency, right? The frequency, the crossover frequency, usually, and then the gain. Now, something else that you see in crossovers is a phase reversal switch sometimes. You can reverse the phase. You can invert it. How do I describe phase for you? The easiest way is look at a speaker. When it's working, it's moving in and out, in and out. When you reverse the phase, it goes out and in, out and in. It goes the opposite direction. Do you understand? Now, in science, in mathematics, if you add, or if you take 2 signals and put one out of phase and join the 2 together, you get what we call a cancellation. Are you with me? And that's why sometimes, you know, when you do a professional setup for drum set, you can have a mic on top of the snare, one under the snare. You have to reverse the phase of the one under. Otherwise, it will be cancelling the sound coming in from the one on top. Do you get it? You see the phase reversal switch in your mixer. Per channel, it's, what do you call that sign? The crossed O, 0 with a cross. Is it? Phi. Phi, yeah. PHI. Phi. So that's a phase reversal switch. So what it does is switch your phase, reverse it 180 degrees. Are you with me? So you have that also on the crossover. Because sometimes, depending on how you locate them, you understand? Depending on how you locate them, they might be out of phase. You understand? From the speaker. Now, as I'm talking, I'm remembering something else. We were tuning some systems yesterday, and some of the drivers were just not doing what we wanted. I realized now that if we could change the distance, we could adjust the phase. Unfortunately, most speakers are not, you can't do that. That's for a higher class. So, basically, the crossover does that. It separates frequencies, right? Okay, if you have more questions on it, we can ask later. What's the time now? 2:08. So we already finished the second section. All right, so I'll briefly talk about the compressor. What does the compressor do? Compressor. That's another of the processors. It's a compressor. What does it do? I have a compressor in my fridge. And the vulcanizer uses a compressor too. Yeah. Incidentally, all of them work more or less the same way. What does the compressor do? It reduces the level, or what I would call the dynamic range of your signal. It takes an input signal and works based on whatever ratio you set it at to reduce the output signal. You get it? Now, why do we need compressors? Is because sometimes when somebody comes in, because of the way you set up your system, they shout. You just see all your system go to red. Now, you don't want that happening all the time. So you put a compressor on the mic. When the person is not shouting, nothing happens. But the moment the person shouts, the compressor just pulls it down. Now, how much it pulls it down depends on what you set it to. If you set it to ratio 2:1, it means when that person singing increases by 3, only 1.5 goes out. If you do 3:1, when the person increases by 3, only 1 goes out. If you do 6:1, when it increases by 3, only 0.5 goes out. Do you get it? That's the work of a compressor. Now, there are a few parameters that you worry about. The threshold, which is the point at which the compressor starts working. The ratio, which is how much level. That's when I say 3:1, 2:1, 4:1, 5:1. When it gets to 10:1, the compressor becomes a limiter. You understand? That's like limiting. So no matter how much you shout, the signal doesn't get higher again, depending on where you set it. So then a few other parameters are the, what do you call it now, the attack and the release. Attack is how quickly it starts compressing when you reach the threshold. The release is how long it takes to drop the compression after the signal has dropped below the threshold. You understand? And there are a few other things. There's a hold and all of that. So you can, the rest is simple. Gate simply shuts the gate. Abi? Gate is open and shut. When your signal is below a certain level, the gate closes. When it rises beyond that level, the gate opens. Why do you need a gate? Sometimes, I was talking about miking the drum set. You can put 12 microphones on the drum set, or more, if you want. But if all of them are open at the same time, all of them are contributing. Not so. But now, you don't want the tom mic to be working when it's not hitting the tom. So you put a gate on it. So until it hears sound, before it opens. There are other applications of that, but that's a gate. Okay? Let's leave gate. Gate, you have threshold to worry about. Threshold is the only thing, when it reaches that threshold, then the gate opens. So if you reduce the threshold to the very minimum, the gate is doing almost nothing because everything can pass. If you raise it very high, the person will have to start talking or shout before the gate opens. And you see the phenomena. If somebody talks quietly, if you have a pastor that doesn't speak very loud into the mic, like I know some preachers that hold their mic here, Do you understand? If you put a gate on that mic, you are likely to have it cutting off, depending on where you set the threshold, cutting off the person's voice. You understand? So that's the work of a gate. All right. Anything else among the processes that we've not talked about? Effects. Effects, you don't need to talk about it. Effects is effects. Basically, you want a voice to sound like it's in a large hall. You add a large hall effect. Do you understand? The only thing is you need to know you usually have to consider the ratio of the direct signal and the affected signal, the one we call the wet signal. The ones you add effect to is the wet signal. So most of the time you need to balance it. You don't want too much of wet signal coming out. For instance, when somebody's talking and all you're hearing is the reverb of his voice. Do you get it? So usually you want to adjust that. So there are various effects. There are various ways to even change the effects that you see. There's also what we call a multi-tap delay, where you talk and the person's voice comes back. You've seen it in some of these adverts and some of the music, where the person says something and it repeats back. Now, depending on how fast you want it to repeat or how many times, you understand, you can set it on your effect. There's also the one we call chorus, when one person's voice is doubled in several ways. Those are the different effects you can use to achieve the kind of output that you want, depending on the sound in itself. Okay. Right. I'm going to stop this one there. We didn't talk about speakers, so I'll just talk about it briefly. I've already mentioned that the different speakers project different parts of our audio spectrum. Okay? The high frequencies, like I said, right down the middle, do the high frequency signals. That's where the and the clarity of your sound is. If the tweeters in the speaker are not working, what you'll be hearing will be something similar to this, where you can't make out. The system is still loud, but you can't make out all the S's, all the T's, you understand that I'm trying to say. That's a high frequency. Usually between 2 kilohertz and 20,000 is high frequency. The mid frequency is projected by woofers from about 4 inches in size all the way to 15 for woofers. That one down there is a 15-inch speaker. You understand? These ones up here are 10 inches. 10. That's for the mid-range. Then the low frequencies usually start from 10-inch also, all the way to 24. These ones are 18. You understand? So the naked speakers, depending on their size, are meant to project different parts of the spectrum. Are you with me? Now, what you discover is the wavelength of the different frequencies, right, differs. The higher frequencies have lower wavelengths, that's shorter wavelengths. The lower frequencies have larger wavelengths. Now, the wavelength, the bigger it is that the wavelength is, the further it's able to travel despite obstacles. But the shorter wavelengths, which means the higher frequencies, are not able to travel far if there are obstacles. It's like the difference between when a trailer hits a wall and when a beetle hits the same wall. If the wall is thick enough, it will stop the beetle. But if it is, no matter how thick it is, it's not likely to stop the trailer. Do you understand? So that's the difference between the small wavelengths and the large wavelengths. Small wavelengths, all it takes is 1 or 2 people to stand in front of that speaker. The person in the third row will not hear it. But the lower frequencies, because of the large wavelength, right? Even if you are standing there, you'll still be hearing the bass at the back. And that is why, when you are setting up your speakers, you put high frequencies in a place higher than the level of the human beings, so that the sound is able to travel. Now, the lower frequencies you put right at the bottom, it doesn't matter. Even with everybody standing in front of you, he will find his way to bend around, and you'll still hear it at the back. Do you get it? So that's what happens. Now, in a church, I'll give you an example. The first time I did sound in a big crusade, we put the speakers on the floor around the door, and everybody was sitting. Now, when they sit and the preacher is preaching, everybody hears him. The moment everybody stands up, We don't hear anything again. So it was like, what's happening with the sound? That time I did not know that we needed to raise speakers high. I didn't have the benefit of this. I didn't attend any classes. Do you understand? So the preacher called and said we should go and get horn speakers. And we were like, can you say horn speakers? We know how horn speakers sound like. So it was then I realized that, okay, can we put them up a bit? So we went and looked for stools. And we put the speakers on stools. And the problem went away. So people stood and they could still hear. You understand? We could hear the bass and everything, but we couldn't hear the preacher talking. That was simply because the high frequencies didn't have a way to travel. So we always place them above. Now with loudspeakers, please remember, there is what we call the dispersion angle. That is how wide it projects its sound and how in the vertical region and in the horizontal, how wide it projects its sound. So when you are placing it, you want to place it in such a way that there are the least obstacles in front of the speaker. As a rule of thumb, everybody that sees the speaker hears the speaker. You get me? If you don't see the front of the speaker, you are seeing only the side of the speaker, you are likely not to hear very well. Why? Because the high frequency is usually right in front of the speaker. Do you understand me? So that's about that. Now, because the time is far gone, do we have questions? Do we have questions? We do. Okay. Just one more thing before I go. This is for the advanced class. I was going to talk about setting up your sound system in your church and also about gain structure, what we refer to as gain structure. I was going to talk about it, but my time is almost up. So let's look at it quickly. For a setup, when you want to set up your sound system, there are various things you need to take into consideration. We didn't talk about cables, but let's assume that everything is good. Your cables are good, your microphones are good, your amplifier is good, the speakers are good. Once you enter into your setup, you want to make sure everything is connected up properly. The microphones are connected to your mixer, the mixers are connected to your processors, the processors are connected to your loudspeakers. You get into the hall anytime, even if it's your system, the one you use from Sunday to Sunday, you want to check that everything is connected properly before you switch on the system. Do you get me? Errors that you can correct before you switch on the system could damage your system if you are trying to correct them after the system is switched on. So you want to check. Now, once everything is connected, you want to do what we call a line check. Oh, before that, you want to check the system output itself. You want to make sure that all your speakers are still working the way they're supposed to be working. Reason for this is simply that if they're not working the way they're supposed to be working, what you're hearing will be different. Your snare may start sounding like it's bad, for want of a better word, simply because the system is not set up properly. Do you understand? So you want to put on the system, you want to make sure that all the high frequencies are working as high frequencies, the mid frequencies are working as mid frequencies, the low frequencies are working as low frequencies. Okay? That's the primary thing. The second thing is you want to do your line check. What do I mean by line check? Every single channel is working the way it's supposed to work. The pastor's mic is not coming out of the lead singer's channel. The lead singer's channel is not coming out of the talking drum channel. We want to do that line check. Then you also want to make sure that all your mic cables are still in order, okay, before the service. Now, the things that you can correct, that you can repair, that you can adjust, that you can change before service, when it happens during service, they point you out as a bad engineer. Are you with me? If you have to run around when program has started, then you are drawing attention to yourself. How many of us know that if the engineer is very well known in a church, it means the sound in that church has trouble? If your pastor calls out your name on the altar all the time, it means the pastor is uncomfortable. Okay? The very good sound engineers are not even known in their church. Do you get it? Our job is to work in the background. If you want to be in the foreground, take a mic, go sing. See? Right. So that's the case with the setup. So you want to do your line check to be sure that everything is in order. The wireless microphones, you want to be sure that the batteries are new, or at least that they will last the service. No point preacher getting to the middle of the sermon and the battery goes off. That's when he will announce your name to the church and ask whether you are a vulcanizer or a sound engineer. I know, I experienced that. So, you want to be sure all of that is in place before you start. And then, if possible, you can now do what we call a sound check with the instruments or the instrumentalists. Now, that's also a very important part of it. You need to learn how to work with the ministers. By ministers, I mean both the pastor, the singers, and the instrumentalists. The moment there is no respect between the instrumentalist and the sound engineer, you will have trouble. But the moment the musicians see you as somebody who knows what he's doing and who also listens to them, even when there is trouble, you will see that they are not going to fight you. They are not going to be angry at you. Do you understand? We've seen in live sound situations who are the most troublesome people. The talking drummers, the percussionists. They are usually very troublesome. And why? One day I found out there was a talking drummer who would normally give one speaker like that in church. Then one day I saw him playing alone outside. He had 12 speakers behind him. When I looked at that, I said, how will he ever be satisfied with one speaker in church? And you need to see or to hear what the guy was doing with the talking drum. Just him alone. He did all sorts of things. I mean, I was impressed with his sound. So I could understand. When he came back to church, I had to explain to him, sir, we cannot give you that kind of sound that you got outside. We don't have that kind of. You have to share with everybody. And he said he understood. After that, he never worried me again. He says, okay, I want low frequency, we give him. That's the best I can give you. Okay, we'll manage it. But if there was no understanding, he keeps wanting that one that he heard outside. And he can't have it in church. Because if I do that with every talking drummer, what happens to the rest of the congregation? We'll fill the whole place with speakers, not to. So, you want to do that. You want to do your work. And also, you want to know your equipment. So that the moment you see or you hear something, you already know what is going on. You don't need to do trial by error. Do you understand? There are sounds you hear, you know, okay, that's the cable. Other times, you know, oh, that mic is bad. Or amplifier is the one causing the trouble. Do you understand? So study yourself. Study all your equipment. Study everything you can find out about sound. Are you with me? So that anytime you are doing any of these things, you can. And finally, I'll just talk briefly about gain structure so that we can ask questions. We have only about 4 minutes left. I'm sorry about that. Gain structure. When you are setting up your system, the easiest way to talk about gain structure is make sure that your signal is not going into red at any point along your signal path. You have indicators, you have lights to show. You don't want that peak light showing at any point. You want to get the maximum you can without the peak light showing. You understand? That's the easiest way. Once you set it up like that, you probably have a good gain structure. It's much more involved than this, but I can't go into details of it without spending so much time. So now, let's go into the questions section. Yes. There's a reason for it, yes. There's something we call coupling. Coupling. Coupling means if you have only one speaker, right, there's a way it projects. Then when you put two together, there's a way both of them will project. Are you with me? There's a way both of them will project. Now, with two speakers, remember, when I said the high frequency has, what do you call it now? Short wavelength. For two speakers to couple, the wavelengths, you understand, this distance between them is a relation to the wavelength between the two speakers. Are you with me? So now you'll see that the high frequencies are all right next to each other, right in the center, because they are the shortest wavelength. You understand? So they are placed very close together. Now the mid are further apart. Do you understand? Because the wavelengths are larger. So it's easier for them to couple together from a distance. The sub are even further away because their wavelengths are that much larger. So they will couple better. Do you understand? So that's why it is like that. That's the advantage with the array. Okay? Next question. No more questions. Okay. Gain structure. When you are setting up your mix, sometimes you set it up for just 5 microphones, 12 microphones, and more. Now, the more the microphones you are using, the higher the addition becomes. If you're using only one microphone, you can have gain on that one microphone up to maybe 30 dB. When you are using 2, you've got to drop the 2 so that when the 2 are adding together, they don't overload your preamp. Do you understand? When it becomes 4, the gain for each one has to drop. Do you understand? Now, every single thing on your console all add to the gain outside of the console. Do you get it? So what you want to do is look at the number of microphones you are using will determine how much gain you can get from each mic. And now, you are going to set up the gain in such a way. There's something called the noise floor or noise of your system. For your signal to be good, your signal level has to rise above the noise floor. Do you get it? But even more so, above the ambient noise of the room. If the room is very noisy, your speakers have to become very noisy too. For it to have good quality sound, it has to go above. And that's also another reason why on your stage or your altar in church, you need to lower the level of noise. Because for the PA to sound good to the people at the back, it has to rise above the noise coming from your stage. You get my point? So, and that's why in some churches you see they put the drummer in a cage. It's the loudest instrument there. But that also affects your gain. You understand? So one, how do you set gain for a microphone when you first put on a console? When you have set up your amplifier, you've opened it up, you've played music through it, the system is sounding good, okay, the way you want it to. Then you come to the mixer. My way is to put the fader at 0 with the gain all the way closed. Do you understand? Then you stick into it and start opening the gain. You understand? Until you have enough level for that one microphone. You understand? Now, notice I did say, if you're using only one microphone, pastor's mic, you can have as much gain because it's the only one that's talking at that time. But the moment musicians and all that come in, then something has to give. Do you understand? Lead mic can be at a gain a little higher than the others because you want to hear him a little higher than the others. But the others cannot be close to his own gain because it means when 6 of them are singing together, they will swamp the lead mic depending on where you set the gain. Do you understand? So what I'm saying is the more microphones you have, the lower the gain of each one needs to be so that the contribution at the end of the day gets to the level that you want without overloading any of the inputs. You understand? So what you want to do is keep your signal in the green. from the beginning all the way to the end. Okay? So that's more about the gain. All right. Yes.
Does the size, does the weight and material used to make the speaker affect the sound? And if it does, how?
Okay. Does the size and the material used to make the speaker affect the speaker? The weight. The jury is out on the weight. Let me explain why I will say that. Some of the speakers themselves have different weights. Although I've discovered that the newer types of speakers now, I don't know the kind of technology they put in them. They don't use the kind of heavy magnets that we used to have. I think they found a way to use a reverse engineering where the same sound in itself is adding to the flux that moves the speaker. But be that as it may, there is a certain box volume that fits the frequencies being produced by a speaker. In other words, the smaller boxes will fit only smaller speakers. The bigger ones tend to have, you understand, bigger speakers. But you'll see that most 15-inch speakers are around the same size, which means by the time they do their calculations, the volume of the box gives them the same results. It's a bit like when you talk about aerodynamics. All cars very soon, the faster they go, the more close the shape is. You understand? The closer the shape is. All of them are like the same. The Lamborghinis, the Ferraris, they all have the same basic shape. You get it? So all they do is add frills to make the difference because the aerodynamics is the same. It's the same air. It's the same wind tunnel that all of them are using. So the same thing with speakers. It's the same parameters that they're using. So there's a standard volume that goes with the size of the speaker you're talking about. Okay? So that's that. The weight in itself, like I said, doesn't really matter. Much of it is from the speaker. But there's also something else you need to consider. If that speaker, for instance, subs, is made out of plastic, low frequency, for those of you who sit in front here during concert, how do you feel? Do you feel the thump on your chest? Which means it has energy in itself. If the box is not heavy enough, you'll see the speaker dancing. Or you've never noticed that? You see it dancing. I've seen situations. Oh, it's been. Thank you. Now, when the drummer monitor, I understand, will have the tendency to fall off. Because as it's working, it's also moving. Because the drivers are moving, they are moving air. You understand? So if it's not heavy enough, you have that kind of event happening. But some speakers are made with plastic. And plastic is necessarily lighter. Not so. What they use to ameliorate that is they have this, what do you call it, top hat, the hole under them, and you put them on a stand. So it's the stand that holds the speakers in place, not the weight of the speaker itself. Other times they have what they call traction pads under it. You get it? To stop it from moving around like that. That's the only thing I think the weight does. Now, for the older systems, before the neodymium magnets came up, the magnet themselves had to have some standard weight for them to be able to produce the particular frequencies that the speakers were supposed to generate. But all of that is changing now. With more technology, more research, they're able to find, you understand, lighter things that does the same work. Does that answer your question?
Check. Okay. We were talking about the reverse mode of speaker.
The
reverse. I don't know what does it do when you put your... We're talking about reverse. I didn't really understand it.
Inverting the phase. When I say polarity reversal, okay. Have you heard of a cardioid arrangement for subs, for instance? A cardioid arrangement. What do you understand by it? Okay, I will explain. The sub by itself is an omnidirectional radiator. When it's working, you hear the low frequency all around it. You understand? Now, in an elaborate setup, in some of my setups, I have 16 subs. 16 of these in one spot. Now, if you have 16 in one spot, you can imagine the weight of sound that's going back to the stage. Do you get me? And sometimes it makes the stage uncomfortable. They can't hear anything because all of it is low frequency. So you want to do something in such a way that the sound that goes to the back is lower than the one in front. And by so doing, we do a cardioid arrangement. A cardioid arrangement is made with 3 speakers. 2 of them will face the front, and 1 of them will have its polarity reversed, the phase reversed. The effect of that is it cancels the sound going to the back. Do you understand? It cancels the sound going to the back. It's not easy for me to be able to explain it to you, but if you know what sine wave is, most of our electricity is in form of sine wave. So you have the waves going that way. Now, an inverted phase goes that way. The main one goes that way. The inverted one goes, you understand, from up, down, from down, up. Now, when you add the 2 together, they cancel out. You understand? You get a straight line. If they are exactly equal in amplitude, you get a straight line. You understand? So, but now, when you have multiple speakers like this, if maybe one of them got damaged and somebody repaired it and then they connected it and they put one in reverse phase, you will suddenly hear that instead of the speaker, the whole thing, if there's only one that's reversed in that system there, instead of the whole thing sounding good, it starts sounding like it's coming out of tin. Do you understand? That's the effect of reversing the phase of a particular speaker. Now, the same thing happens with microphones. In a situation where you're using many microphones for one event or to pick up one sound, like I mentioned, having 2 on a snare drum, 1 up, 1 down. If you don't reverse the phase yourself, the mics are in opposite directions, so they're hearing opposite sounds. You understand? In your mix, you will just be looking for the snare, it won't be there. It will cancel. Yes. So, and you find out that when you switch off one of the mics, the sound will suddenly come up. Do you get it? It will suddenly come up. It's because one is in reverse phase, so it's canceling out the other. You get my point? Aha. So that is the reason why the channels on your desk have that phase reversal switch. So when you notice that, oh, okay, when these 2 are together, one cancels, you just reverse the phase of one of them. Just hit that button. It will reverse the phase automatically. And then the sound should come up. You understand? Then in a multi-speaker setup too, the same thing. If you start with 1 speaker, put on the second one, the sound should increase. The moment you put on the second one and the sound reduces, the second one is doing something bad. Or one of them is bad. So you find out which one is in the correct phase. By the time you add the 3rd one, the same thing. If you have 4 of them, and you do 3, and all 3 have added, by the time you put on the 4th one, if it's in reverse phase, all of them together will sound less than 1. Do you get it? So, so in such a case, if it's reversed, what you need to do is to find a way to reverse the phase. Now, it also happens when you use an amplifier in bridge mode. Are you with me? Wavedale amplifier, the MP28, for those of us who know it, it has a bridge mode connector in the center. But for those of us, when you know what you're doing, I have only 1 signal. And I want to power the 2 speakers. So I send only 1 signal into channel A and put the amplifier in bridge mode. Now, if I don't reverse the phase of one of the speakers, the 2 of them start sounding amadusinu. Start sounding as if the sound is going inside, it's not coming out. Do you understand? So what I do is I know that when you put an amplifier in bridge mode, what it does is it takes 1 signal, 1 amplifier, it takes the second one, inverts the polarity, and adds it to the first one. You understand? In mathematics, it's a bit like you have a sine wave, you understand, the one I'm talking about, and then the other one going in the opposite direction. So the peak-to-peak voltage is what the amplifier is using. That's what is responsible for the amplitude of the sound. You understand? But that is only when you connect to 1 end of one and one end of the other. But in the case where I'm using it as stereo amp with a bridge signal, you understand? That's what the amp is doing. But me, I know. So what I do instead is I reverse the phase of one. So I'm still taking from the center rather than from across the peak. You understand the difference now? So in such a case, I can just turn the polarity of one of the speakers, and I still have my speakers talking in phase. But for somebody who doesn't know, they come the next day, Abby, and just put the speaker and put it in the correct way. They will just see the speaker that is not sounding good. Do you understand? That's creative use of polarity. Okay. Any other questions?
Concerning the bridge you talked about with the use of amplifiers, I read that when using bridge with amplifiers, that for clarity, that it is better to have both the positive and negative on cables on both positive of the two channels.
It's not really for clarity. It's the same thing I just talked about. You understand? It's a bit like your touchlight. You understand? If you have, many of us did that experiment when we were smaller. We have a bulb and two batteries. Not so. When you put the bulb on one battery, it's bright. When you add the second one and you put the wire at the other end, Abby, it becomes twice as bright. That's exactly what happens in bridge mode. You understand? The two amplifiers are working as one. So it's as if you take one amplifier, take the other one, turn it, and join it to the back of one, and then take your signal at the ends of the two. But because it's reversed, you take it from positive of one and positive of the other, rather than positive of one and negative of the other. Do you understand? Now, in sine wave, like I said, it is the peak of the top signal and the lowest depth of the lower signal. So you have that voltage difference. That's what is responsible for the amplitude that you get, which is twice the amplitude. I don't know whether you understand what I'm trying to explain. That's what happens. So you need to, they will tell you how to wire it. In some amplifiers, they have the connector separately for bridge mode, which is already wired properly for you, so you can use the same cable. But in normal amplifiers, if it's binding post, they will tell you connect plus of channel A to plus of channel B. Do you understand? So there's no center. You understand? Yes.
Sir, can you please talk more on amp to speaker connection, combination, wattage and ohms? So that
okay. When I said we didn't talk about speakers, that's where we would have been talking. But let's talk about it. Most speakers will have what we call a nominal impedance. The manufacturer would have worked it out. You notice what's happening with my sound? I am here. I'm nearer the speaker. So the sound is changing because the mic is beginning to hear the speaker. Okay? So now, speakers have nominal impedance. It will be written at the back. Sometimes it's 4 ohms, sometimes it's 8 ohms. You understand? Mostly, like that single one there, it will be 8 ohms. It's the most common that we use, right? Now, they will also write the wattage. They will write RMS, like that one, maybe 400. And then they will write peak, 800. And then sometimes they will say continuous, 200. Are you with me? Now, when you take one speaker, 8 ohms, 400, and you add a second speaker, depending on how you wire it, you understand, the overall impedance will either be 4 ohms, remember 8 ohms, 400. The overall will be 4 ohms, depending on how you wire them, 4 ohms, 800, or 16 ohms. 16 ohms, the same 800. What's the difference? Depending on how you wire it. If you take, normally speakers have plus, minus, positive, negative. You understand in them. If you join the two together, you can either have positive to positive, negative to negative on the same wire, and then the amplifier is seeing just positive and negative. Or you take positive, right, to the amplifier. You take negative to positive of the second speaker, and then its own negative to the amplifier. What have we done? Let me go over it again. Positive, negative, right? So you take positive to the amplifier, negative to positive of this one, then negative of this one to the amplifier. Series. This one is series connection. So the overall impedance is 8 ohms plus 8 ohms, 16 ohms. Do you get it? The amplifier is going to see 16 ohms. So the power the amplifier is going to deliver is the power of that amplifier at 16 ohms. If it's a 5,000 watt amplifier, at 16 ohms, it will probably do 2005. Do you understand? To do 2005. But if you do positive, positive to the positive of the amplifier, negative, negative to the negative of the amplifier, then the two 8 ohms become 4 ohms. You get it? They become 4 ohms because it's in parallel. So the amplifier will see 4 ohms. So its power will be the power into 4 ohms. If it's a 5,000 watt amplifier, which means 2,500 into 4 ohms, then the speakers will see 2,500 watts. In the case where it's 16 ohms, for a 2,500 watt amplifier, it will probably deliver maybe 1,000 into 16 ohms. So the speakers will see only 1,000 watts. Do you get it? So depending on how you connect your speakers, the amplifier will see the impedance, and it will deliver the power it's meant to deliver into that impedance. Remember, I did say that the lower the impedance, the more the amplifier works. An amplifier that delivers 400 watts into 4 ohms will likely deliver 600 or 800 into 2 ohms. Do you get it? And that same amplifier will deliver 200 watts into 8 ohms. Like half the power as you double, you understand, as you have the impedance. More, double the power. Okay? You understand it? Okay? Does everybody understand? So once you connect in parallel, you are increasing the work from the amplifier. When you connect in series, you are reducing the work of it. But the difference is that when you connect in series, if you remove one speaker, the whole system will not work. Remember, because you are joining them to each other. But with parallel, when you pull out one, the rest will continue working. I hope you understand. Okay. Yes. Any other question? Yes. Yes, Mike.
What effect like will be like what effect will it be to the output if one drives a speaker with an amplifier that has a lower wattage to it?
Okay. I'll explain that. He said, what will be the effect if you drive an amplifier with a lower wattage than the speaker? Every speaker is meant to take a certain amount of power to produce its best. You understand? When you drive with a lower amplifier, you are more likely to destroy something. You will burn something. Because the speaker would not sound good enough, even when the amplifier is delivering all it can deliver. You understand? It won't be loud enough. So you crank it all the way up and you keep pushing. When you push an amplifier and it starts showing red, it goes into distortion. You understand? If it doesn't go into distortion, you are fine. But the speaker will not sound its best. So most of the time you'll be looking at the speaker, you could do that. So you'll be tempted to increase volume. Do you get it? So that's the basic thing. Usually engineers would drive loudspeakers with amplifiers that are bigger than the loudspeaker and use limiters to make sure that the signal doesn't rise to the peak. Do you get it? So that the speakers always sound good. That's just the difference. Okay? All right. Now, I will encourage you to do something. Whenever you want to purchase an item or whenever you actually purchase an item. Even if you didn't purchase the item, if it's your pastor that went to purchase it, once they bring it, ask for the manual and go through the manual. You understand? The manual will tell you everything that the system or the speaker or the device can do. Even your microwaves, your deep freezer and all, they all come with manuals. Which tells you, one, the voltage at which it runs. We tell you how much power it draws. You understand? That's how it's possible for you to put things together in your house and you know what kind of stabilizer can carry it. Or you can calculate how much light you are using, in short, from your meter, because you know already what wattage. Now, for your microphone, you'll see the sensitivity figure. You'll see the impedance of your microphone. You understand? And before you connect to the mixer. Now, in recent years, it's getting better now, but it used to be so bad that in the market, we had a lot of China products. Now, don't get me wrong. It's not that China doesn't produce good things. China produces good quality equipment, whether sound or household equipment. What is wrong is when the Chinaman has been told to produce a different quality from what is written on it. So you buy a 5 kVA stabilizer, but inside it, they put a 2 kVA transformer. So when you think you have a 5 kVA stabilizer and you're trying to drive it to 5 kVA, it will die at 3 kVA. Simply because the inside component has been reduced. You understand? And because of this, a whole lot of our gear, you know, you've heard the Electro voice, RCF, PV, JBL. You understand? In the local market, there are a lot of fake JBL, for instance. You will see UBL, you will see the J with a dot on top and all of that, and they sell it to you as JBL. Now, it's supposed to do what JBL does. But remember, if it will do what JBL does, it will be called JBL. The fact that it's not called JBL means it is not going to do what JBL is supposed to do. I don't know whether you understand what I'm trying to say. If somebody produces a fake one of this and is supposed to do exactly what this one does, it will cost them the same amount that it cost the person who did this to do it. So they can't sell it to you cheap. So what would be the essence of doing a fake one? So why do we do the fake one? Because we reduce the quality of what is inside, but we sell it off to you at the high price. Do you get it? Or maybe at a lower price, but we reduce it so far. So what you are getting is actually a shadow of what you think you are getting. You understand? So because of that, we encourage you, buy from reputed dealers, the ones who are actually representing their own companies. You understand me? Because then, if anything happens, for instance, if you buy an RCF speaker, it comes with a serial number. If you go on the site of RCF and enter that number, it will bring out the speaker. If it's genuine, you will know. Do you understand? You will know it's genuine. If it's not, then it won't show. Are you with me? The same thing with microphones, with any of the manufacturers that you want to buy from. You want to be sure that you are getting that quality. Until we start producing in Nigeria, the best you can do for yourself is to buy the quality that you know you can rely on. And usually, manufacturers will be able to support their own, what do you call it now? Their own dealers or their distributors, which means you buy something, it goes bad. You can always get support from the factory that produced it. Are you with me? Especially when it's still under warranty. All right. So, any more questions? Any more questions? No more questions. Okay. Are we happy with our lectures? Thank you very much, all of you. Let's pray. Father, Lord, we thank you for this hour. We thank you for the fact that we were able to share together so that our work in your vineyard would improve. Our Father and our God, we ask that everything we have learned in here, O Lord, let it be a seed planted in our hearts. Let it grow within us, O Lord, and bring forth good fruits in our work in your vineyard. And Lord, for each and every one of us represented here, O Lord, we ask that we do not miss our reward, O Lord. Guide us and help us, O Lord. Keep us from distractions, O Lord, and help us to stay focused in the work of your kingdom. And at the end of the day, O Lord, let us all have joy by being admitted into your kingdom as good and faithful servants. Thank you, everlasting Father. Lord, we ask, O Lord, that you meet every one of us, O Lord, at the point of our need. Lord, show us your way forward, O Lord. Thank you, Father. Blessed be your holy name, O Lord. In Jesus' name I pray. Thank you, everybody.
Thank you very much, sir. Can we please put them together for our facilitator once more time, please? Thank you so much, sir. Okay. So I'm sure he asked us if he had questions. So it's my time to ask for a recap so we can be very sure that we're not following in an opposite direction, if you know what I'm talking about. When you were given a baton to go in this direction and decided to. Praise God. Okay, so quickly, we would just tell us your name, church that you fellowship with, where you attend, and what you do. If you do this professionally, so let's know. And what you've learned in the course of this workshop. So who would like to go first? Or I should just choose a random. I would just love to choose a lady because what have you learned the course of this workshop? Your name, tell us your name, what you do. Yes.
I'm Ogujide Adeshawa.
Okay.
Actually, I'm a chorister.
Okay, good. Please use the mic,
I'm Ogujide Adeshawa by name. And I said I'm a chorister, actually. So, and okay, we were told uses of some instruments in hall, the microphone, the mixer, and all types of microphone, all sorts. And he advised that if we are getting products or something, that we should go for quality. And I know, Sha.
Okay, Adeshawa, as a chorister, you're in a choir, right?
Yeah,
That's what you
yeah.
said. Okay, so I'm sure one thing that really applies to you as a chorister is that thing you're holding, right? And then he spoke about it. So tell us, how, from the workshop, how does that microphone, in terms of some of the things he has said, what are some of the lessons you've gotten about the microphone?
Okay, we were told how to handle the microphone.
Okay,
You get
which should be?
like this or something.
Okay.
And we shouldn't cover the mic
Okay.
like this, you know, it will affect the sound.
Oh, okay, good.
That there is this.
Use the mic, use the mic.
And there is this, what did they call it, Seth? I've forgotten, something that serves as maybe cover or something, I don't know.
Okay. So what was that called? Who can help out with that? That thing, like she said, that wind shield.
Yeah,
Windshield,
yeah.
okay.
Thanks, bro. So, okay. So that we are advised to use it whenever we're using the microphone. So it will absorb all the saliva and all.
Oh, okay. Good. Thank you very much. Can we please students get out for the show, please? Thank you very much. So who else would like to go? Okay. No. Just tell us. Don't just pass it. Use it.
Praise God.
Hallelujah.
Our facilitator started with Okay, my name is Steven. Ademilego Steven, UJCM. Our facilitator started with the type of.
No, can you tell me what you learned?
Okay, what I learned.
Yes.
Okay. I learned many things actually, but I also learned that. Okay, let me go to the processor aspect. That there are many there are many type of processors. We have the EQ, the equalizers, the compressors, and we have the dockers, we have the gates, and like that and like that. So the EQ actually works like we have two type of EQs. We have the graphic EQs and we have the parametric EQs. And the graphic EQs are the ones we know actually, and they are called graphics because we see them. So check. Okay, like when we work on the EQs, there are three things you should look for. We have band, the band length, like our frequencies, our high, mid, and low, and we have how we move them. The gain, then there's one other thing like that. So, and it is used to filter out our sound. Okay, that's compressor. If I'm correct. So it is used to set quality to to get a fine tune to what we hear. And I also learned that okay, when using the mic, there are several types of mics. There's a condenser mic. There's the normal dynamic mic. And when we are using the mic, we should first know the type of mic we are using. There's the omni sound. Then we should know. Then we should check. So uh, we should know how to position the mic.